Hello and welcome to this EE328 lecture video on discrete time convolution. We are going to use convolution as one of the tools that enables us to calculate the response of an LTI system, the response of a relaxed LTI system to an arbitrary input. So the response of a relaxed system to an arbitrary input is also known as the zero state response to that input. And the reason behind this is I think it's easier to see in discrete time than it was in continuous time. In particular, by definition, if the unit impulse or unit pulse or unit sample is applied to the system, and my notation for that signal is d of n, then by definition what comes out we call the impulse response, which gets the symbol h of n. So if I were to scale the impulse, so this instead of being height 1 is now of height x of 0, where x is some arbitrary signal, and at time 0 it has some value, and I'm saying let's take that value and multiply our unit impulse, and we get this signal, then I'm just scaling an input, and linearity tells me that to get the output, all I do is scale the output by the same scaling factor. Okay. Likewise, if I have another sample with, say, a different amplitude, call it x of 1, if that happens one sample after sample number 0, then I can represent this input signal as the sum of two unit samples. So this is now, we're adding this signal with that signal. And because the unit sample is 0 for everywhere other than when its argument is 0, these only apply at the points in time where their arguments are 0. So this only applies at n equals 0, and this one only applies or fires, whichever terminology you prefer, at time n equals 1. Okay, so now I've constructed a new signal out of two unit samples that are scaled and shifted. Now that sounds a lot like linearity and time invariance. In fact, it is. I can get the response due to this new signal by adding scaled and shifted impulse responses, and that's the power of LTI-ness. And so I hope you can see that if the x signal is arbitrarily long, as long as it's composed of discrete samples, positive or negative, could be 0, as long as these samples occur at regular time instances, I can always write x of n as the sum of scaled and shifted unit impulses, which means the output due to x of n will always be the sum of scaled and shifted impulse responses, h of n's. Okay, so we can, that same statement held true in continuous time. I think it's just much harder to visualize how an arbitrary continuous time function can be comprised of Dirac deltas, but actually the same exact verbiage can be used. So what we just established is that an arbitrary function in discrete time can always be written as the sum of scaled and shifted unit impulses. Okay, so that's what we have in this first line. Regardless of the shape or behavior of x of n, you can always write x of n as the sum of values times impulses, because those impulses only fire at one point in time. Now there are a couple of features of this expression that I want to call out. In particular, the left-hand side is a function of n, and in particular not a function of k. So if the function on the left-hand side of the equals is a function of n, then the same has to be said the right-hand side. This is also a function of n, not k, even though there appears to be a k over here on the right-hand side. This k is called the summation index, and it plays the same role as the dummy variable or the variable of integration did in continuous time. So when you see summation index, you can think dummy variable, or you can think another term is this variable of integration. And so the idea was if you integrated over a dummy variable in continuous time, the result of your integral wouldn't be a function of that dummy variable. Right? It could be a function of the endpoints of the integral, and that's why we occasionally had t in our endpoint of the integral in continuous time. But that's why we tended to not integrate over t in the integral itself. So here, once you do the summation, there ought to be no more k's on the right-hand side. Okay. Now, what we've got on this slide on the bottom is exactly what linearity and time invariance says should happen, is that if we know that d of n leads to h of n, then we know a shifted d leads to a shifted h, and a scaled d leads to a scaled h, and the sums of inputs leads to the sums of outputs. Those are all things you can conclude after you know linearity and time invariance. Then the output due to input x is going to be the sum of all of those scaled and shifted impulse responses. I do want to call your attention to one more word in this sentence, and that is we are only talking about the response of a relaxed system. So if you want, it makes sense to note that this is a zero state response. This assumes the system was initially relaxed, which is the same as saying the initial conditions of the system were zero. Okay. So this particular operation, this infinite sum of one signal times the other signal flipped and shifted, is what we call discrete time convolution. And I'm going to make a small caveat here, is because in actually discrete time we're going to learn a couple different versions of convolution. So when I say convolution, I will mean this, but occasionally I'll have to differentiate between linear convolution and circular convolution. So I want in your notes there to be a note that this is the definition of linear discrete time convolution. We'll get to circular convolution at the end of this unit. So what are the features of this sum? Well, just like in continuous time, one of the signals has to be flipped. Amberdar uses the word fold, and that's because we're running it in negative k indices, and then shifted. And that's because we're then offsetting it by this value of n. And that offset value, or that shifting value, is the independent variable in the right-hand side. Okay, so just like in continuous time convolutions, one of the signals stayed put, and the other one you had to flip and shift across. It's the exact same operations here. Another way to think about, especially the output of a discrete time system, is at any point in time n, if you were to look at the output on, say, an oscilloscope or a counter or something like that, you would hear, and I'm using this metaphorically, you would hear the echoes of all previous inputs for a causal system. And the echoes of the input at time k, after n time samples later, is exactly h of n minus k scaled by the input at that time. Okay, so this line of reasoning, or this way of thinking about discrete time convolution, will be made more apparent when we do our first example. So there's a big difference in discrete time signals and systems between finite length signals, or signals with finite duration, and those with infinite length. So we're going to start simple, and we're going to start with the convolution of two finite duration signals. So for example, let's take a system whose finite impulse response just starts at 0 and goes 3, 2, 1. It lasts for 3 samples, starting at sample number 0. And we are going to excite that system with an input that starts at time equals -1 and runs for up until time equals 2. And so the problem, or the prompt here, is to calculate the output signal given the input and the impulse response. So the sliding strip method when I taught this class face-to-face, you could actually print these out and cut them out and literally slide them across each other on the table. But I'm going to do my best to approximate that here virtually. Says, take one of your signals, in this case we'll take x, and write it as a function of k. Alright, so all I'm doing is replacing n with k, and so the only k's for which I have non-zero x's are -1, 0, 1, and 2. And the values of x at those times are simply given by what's in the brackets, so 2, 0, -1, and 1. Now I have to do the flip, and so you'll note that this is a reversed version of what was given, so 3, 2, 1. Now these values appear in the opposite order, and that's because of this negative sign, the folding or the flipping, however you want to phrase that. But then it's also shifted, so this is also important, is that I've shifted the h signal in reverse time by -2 samples. And I chose -2 because that's the first integer that puts this strip, which is what we're going to be sliding. This is the proverbial sliding strip. It's the first integer that puts this strip kind of outside of this table. And so remember that another way to think about these finite duration signals is that they have zeros, you can think of them, infinitely in both directions. Okay, so if you wanted to, this strip that we're about to slide has also got zeros in both directions. It's going to be messy if we keep writing those zeros, but at the end of the day, when I have a blank here on the page, you can interpret that as a 0 with no consequences. Okay, so how does one execute the sliding strip method? Well, first reverse one of the signals and then slide it out of the table, and then perform the multiplication. So remember what we're doing. We're summing over k of xk times h of n minus k. So far, I've written that, and I've written that for a given n. What I'm about to do is I'm about to multiply. So that means that for every k, multiply x of k times h of n minus that k. So we do this. We multiply these two rows. Now, the bottom row is all 0, and so I'm going to write the product of that product down here in this row, which is all zeros. So I've done the multiplication step. Now I have to do the summation. The summation means add everything in this strip. And the result of that is y at the given n. And so here I'm going to take the n value here. Remember, this is n minus k. So this is for n equals -2. And I'm going to take this sum and put it in this box. Okay, so that's the first iteration, or kind of the negative first iteration of the sliding strip method. Let's move on. I'm going to clear a lot of this writing because we're going to have to reset the whole slide. So what has happened between the last slide and this slide is that we have incremented n. So now n equals -1. So we are aiming to fill in this box. But otherwise the procedure is the same. We multiply here, and here, and here, and here, and then we sum. That sum gets put in the box. Which box? The n equals -1 box. Okay, so let's try again. You feel free to pause and work it out for yourself. Multiply, 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 and add. Fill in the box. Now keep your eye, I'm incrementing the n each time, which is the formal way of saying I'm sliding this strip across because I'm incrementing it through these different indices. Let's try again. Now we're looking at n equals 1, so I've slid the strip one further to the right. Multiply, 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 add. Slide it one more. multiply, well, I guess if you want, multiply, 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 and add. Put it in the appropriate box. Keep sliding until you are out of multiplications to do. Multiply, multiply, and add. Put it in the box. One more. Multiply, 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 and add. Put it in the box. And so here you see that if I were to increment this once more, this strip would then be outside, and I would get all zeros. And if I incremented it once more, it would be even further outside, and I would get all zeros. So there's no chance of anything coming back around or any non-zero outputs forever onwards. So we are comfortable doing the same thing we did actually to the inputs, and that is saying that y of n, if you like, to write it not in this kind of table form, is a sequence of numbers. It starts at 6. The first non-zero sample is 6, and then 4, and then -1, and then a bunch of 1s, and then a bunch of zeros. And don't forget to indicate which sample corresponds to time equals 0 if you write it in this curly bracket form. Okay, so we have just done our first discrete time convolution. We took a signal of length 4 that started at a negative time, convolved it with a signal of length 3 that started at time equals 0, and we got this signal of length, what is this, 1, 2, 3, 4, 5, 6, that started at time -1 and lasted until time 4. You might ask, well, that's fine, but how do we know that that's actually the right output? But we're equipped with a tool to check this. In fact, if we are given the impulse response and it happens to be finite, remember that term, FIR, that means that the difference equation, so remember that term, the difference equation is just the output is the sum of these filter coefficients times the appropriate time-shifted input. Okay, so if we have a difference equation, then we ought to be able to calculate the output due to an input and potentially initial conditions. But again, we're doing a ZSR, so y of -1 and all previous times are going to be 0. In fact, they don't even enter into this recursion table because there is no time delay in y of n. There is no recursion. But we can still calculate with this method. So the table looks something like this. You set up your n values, you write your x of n values. So when n is -2, x of -2 is, well, 0, right? This is x of -1, 0, 1, 2. So if I'm looking in this slot, that's 0. If I'm looking at previous slots, those are also 0. And so y of n is just the sum of 3 times this, 2 times that, and 1 times that. I get that from the difference equation. Okay, at time n equals -1, then the x signal pops up to 2, but at -2 and at -3, it remains 0. So I take 3 times this column, 2 times the middle column, and 1 times the last column, and I get 6. Now, remember the trick in recursion tables is if we have this increment of time, we can think about these elements traveling down and right. So, in particular, I can put the 2 here and the 0 here because they travel down and right, and I have to check what is x of 0. X of 0, we're told, is 0. And so now I take 3 times 0, plus 2 times 2, plus 1 times 0, and I get 4. At time equals 1, we again shift our register, and we eat in the new value, which is -1. And so I get -3 plus 2 is -1. And now we shift the register again. And we eat in the new value of x, which is the last value that we're given. That's the value of 1. So I have 3 times 1 plus -1 times 2 plus 0 times 1. And I think I get +1 out of that. And now we're out of given values of x. And so we again have to interpret this as padded with zeros ever onwards. But we still have past values of x that influence the output because of the shift register. Okay, so here this looks like 2 times 1 minus 1 times 1, so call that positive 1. And now we're eating nothing but zeros and propagating those zeros through, and we get 1 times 1. And I think, yeah, this clears the register. So we get 0 again. Okay, so you can confirm this with the result on the previous slide, that y of negative 1 is 6, and y of 4 is 1, and after that, and before that, in fact, y of n is 0. So that's my double check that I did the convolution correctly. And the key to this double check was realizing that we can go from an FIR to a difference equation by just writing out the filter coefficients. So this example illustrates a couple of take-home messages and really important things that can help you find your way in the forest of discrete time convolution. And that is the start time of the output signal, so that is the index at which the output signal first becomes non-zero, is the sum of the start times of the two signals that you are convolving. So if we think about this in terms of the example we just did, the time at which h started was time equals 0. The time at which x started was time equals negative 1. And if you were to add those, you get the time that we got y to start, which was time equals negative 1. And that is generalizable. That is true for any start time of h, for any start time of x, including negative infinity. So that's actually a really handy tool. And the same statement can be made about the end times. Just replace start with end in that same sentence. And just to double check, the end time of the h signal in our previous example was n equals 2. The end time of our x was also n equals 2. And sure enough, the end time of our output was n equals 4. The last one is a little bit harder to remember precisely because you have to take one off the result. But the length of x was 4, the length of h was 3, the length of y was 6, which is 7 minus 1. Okay, so that's also generalizable. In fact, if any of the lengths are infinite, the length of the output will also be infinite, right? Because if I add something to infinity, even if I subtract 1, I still get infinity. So that's a handy shortcut to take. And this actually kind of allows you to fudge keeping track of n in the output, especially if you do this in a computer, because you just know at the end of the day, the first non-zero value you get, you can just line up with the starting indices of the two signals that you're convolving. Speaking of infinite duration signals, I hope it's evident that if either x or h is infinite duration, the sliding strip method is going to take you a long time, because either the x is going to be infinitely long, in which case it'll take you an infinite amount of time to slide even a finite duration strip across that, or they're both infinite duration, in which case you're taking an infinite thing and you're sliding an infinite thing across it, so you're definitely going to be there for an infinite amount of time. So this is why the sliding strip method is nice for finite duration signals, and it's nice to kind of explain the mechanics of discrete time convolution, but it's not robust in terms of a more mathematical analysis. So let's take a look at what a closed form analysis of a discrete time convolution might look like. So these are two infinite duration signals. They're both right-sided, so x of n might look something like, could be growing, could be decaying, we don't quite know, we don't know anything about a, and h of n is also, let's say, it's decaying. Okay. But both of these things last forever into positive time. So here is where your ability to manipulate summations and sigmas is going to come into play. So the best we can do at this point is to write the convolution sum in its definitional form. So take x of k, which we are given as ak uk, multiply it by a flipped and shifted h. So everywhere you see an n in the h of n expression, replace it with an n minus k. Done, no problem. So the first thing that we would do, maybe back in continuous time systems and signals, would be recognize that this, what we used to call an integrand, but now is a summand, has indices which make the summand 0. In particular, if I plug in any negative k into this expression, this u of k will give me a 0. And if I add 0 to a sum, I haven't changed the sum. Another way to say that is we can use this step to clip the lower limit. We don't have to consider any k's less than 0 because we know they will produce 0 summands, and so the sum won't change. Likewise, this signal deserves a little bit of thought. If I plot this versus k, then this signal jumps when k equals n, and when n is larger than k, the argument becomes negative. So this is truly a flipped and shifted step. And the reason that I draw this is because it's now evident that if k ever exceeds n, this term will go to 0, which means we can clip the upper limit to n by using this step function. Okay, so same result, but different limits. In this case, n's greater than k will make this term go to 0. In this case, k's less than 0 will make that term go to 0. So we can clean this up and write this as the sum over k's from 0 to n of ak. The uk is 1, so I don't have to write it. I'm not multiplying by 1, times b to the n minus k, and the u of n minus k would also be 1. I'm making one assumption here, and that is n is bigger than 0. I guess technically bigger than or equal to 0. Right, if I'm writing a sum from a small index to a large index, the large index ought to be larger than the small index. Another way to think about this is if n were less than 0, then what would the flipped and shifted step look like? It would be over here, which means for positive k's, the flipped and shifted step would be 0. And so we don't have to assume n is greater than or equal to 0, but we also have to note that if n is less than 0, y of n is null, because we have a step that hasn't turned on times a step that hasn't turned on. Okay, so we'll get back to that at the very end. But let's focus on kind of the meat of this matter, and that is when this is a sensible summation to do. So just like in integrals, when you had a function of a variable that wasn't your variable of integration, you could take that variable out of the integral. In this case, b to the n minus k is the same as b to the n times b to the minus k, which means I can pull the b to the n out of the sum, which is a summation over k. And then I have a to the k times b to the minus k. And because these are not to the same power, I can actually write them as a fraction. So a on top, b on bottom, and that fraction raised to the k. And here you recognize this as a finite length geometric sum from our last chapter. And so I can replace the sum with 1 minus the base of the geometric sequence to the end point plus 1 divided by 1 minus the base of the geometric sequence. And if you like, you can actually distribute the b to the n into the numerator and then multiply top and bottom by b, and you get a nice, nifty, compact expression. Okay, so, and then this is, remember, this is equal to the output at time n. Let's not forget our little caveat over here, and I can compactly represent that by simply multiplying this result by a unit step. That says, do this thing if we are in non-negative time, and do 0 if we're in negative time. So there's my final answer. I think you'll agree that's much faster than the sliding strip method with 2 infinite length strips. Okay, lest you think that it's always so easy, let's try a harder example. So this one looks at first glance the same until you see this big old negative sign there. So now the input is what we call left-sided, and if it's going to be left-sided, then if it's geometric, it's then going to stop, something like that. And so if it looks like this, this drawing actually is equivalent to assuming that A is kind of large in magnitude, so bigger than 1. Because if A were smaller than 1, and if I raise A to a negative n, I would proceed to get infinite size numbers. So I think this example really only makes sense if the base A is bigger, I guess in magnitude, than 1. But let's just assume A is bigger than 1 for now. Okay, so let's say the impulse response is again a geometric series b to the n starting at n equals 0. Okay, so here we have x of k, and here we have h of n minus k. And so what have we to do with our steps? Well, this step function looks like a time-reversed step, and so it is 0 for all k's bigger than 0. So that's why I'm going to use this step to clip the upper limit now. Now let's talk about the second step. The picture here actually looks the same as before. So this is a time-reversed step that steps at time equals k equals n. Now I've drawn here n positive, but n could just as easily be negative, and so that's why whichever is smaller, 0 or n, will end up being the upper limit of integration. Sorry, the upper limit of summation. Right? If I draw the opposite version of this, if n is over here, then we get the lollipops to the left of n, and then we get zeros above, in which case the summation only runs to n. Okay, so this is my compact notation. I'm going to run this sum starting at negative infinity k up to the smaller of two numbers, either 0 or n. So how the heck do you analyze that? Well, I think the easiest way to do this is by cases. So let's try case number 1. And this is when 0 is the minimum. So min of 0n, that is 0. Okay, so now I don't have any ambiguity in the upper limit of my summation, and I can write it confidently as y of n is the sum from k equaling minus infinity up to 0 of a to the k b to the n minus k. And you've seen this game before. We pull b to the n out. Summation runs over the same limits, and now I have a over b to the k. Oh man, I don't like these infinitely negative indices, so I'm going to show you how to do what's called a variable substitution when you're integrating, and it's an index substitution when you're summing. So I'm going to let a new index be the opposite of my old index, which means y of n, still a function of n, is b to the n, but now my sum, when k is minus infinity, m is positive infinity. When k was 0, m is 0, because they're just opposites. And now I have a over b to the negative m. I think a better way to write that would be b over a to the positive m. Okay, so let's put that analysis on hold, because right now we've got an infinite sum, and I kind of don't want to think about that right yet. So let's now move on to case number 2. So put pause on this analysis. And let's move over to case number 2. In this case, it's the other case. So it's either 0 less than n or n less than 0. So I'm going to flip the alligator around. And this is when the minimum operator returns n. Okay, so that tells me that the expression for y at time n now runs k from minus infinity up to n. There's no more ambiguity in the upper limit because I've made the assumption of what it should be, of the same summand, a to the k, b to the n minus k. Same trick, we pull b to the n out. We have our same limits, and a over b to the k. Yeah, that makes sense. Okay, I'm even going to do the same variable sub. I'm going to let m be negative k. This one's going to be slightly more interesting, so let's make sure we get it right. Y of n is still b to the n, and this sum is going to be now over m. When k was minus infinity, m will be positive infinity. When k was positive n, m will be negative n. And then again we flip the fraction and raise it to the m. Okay. So now what? This is an even kind of stranger infinite sum, but the trick that I want to pull is I want to write it in terms of two sums that I actually know how to find. So to call your attention to, well, I guess I can highlight it, this statement. You read that left to right as 0 greater than or equal to n, but if you read it right to left, it's n less than or equal to 0. Another way to say that is n is negative. If n is negative, then negative n is positive. So n is negative by assumption, which means negative n is positive, which means I can extend this sum to run from 0 to infinity if I then subtract off the extra stuff that I add. Okay, and then both summands are the same. Let me walk you through that again. This sum up here starts at a positive integer. If I extend the sum to start from 0, then all I have to do is subtract off the extra stuff that I have included in this first sum. Okay, and then I get equality between the sum on this line and the sum on this line. Now, why would anyone want to do that? Well, because we have just created a finite geometric sequence, and we actually have the exact same infinite geometric sequence that we had in the other case, which brings us to a reminder on how to calculate geometric series that are infinitely long. So let's define the infinitely long geometric series sum as the sum of an index running from 0 to positive infinity of a base to the k. If I split out the first term, that's r to the 0, call that 1. And now the summation runs from k equals 1 to infinity, r to the k. And this sum is the same as r times our initial sum. And then I can solve this for s sub infinity, and this is the familiar formula 1 over 1 minus r, where we ought to include the caveat that r can have a radius no bigger than 1. Otherwise, if this is not true, then this original sum doesn't converge, and so there's no point in writing a finite number as an answer here. Okay, so we're going to use this infinite geometric series trick as well as the finite geometric series trick from last slide and last lecture to simplify both of these answers. So on the left, I'm now going to unpause, and I have b to the n times this infinite sequence, which I can write as 1 over 1 minus b over a if the magnitude of b over a is less than 1. Okay. On the right-hand side, this is b to the n times, well, the exact same thing. This is 1 over 1 minus b over a, provided this is true, minus the finite geometric sequence. So that gives us 1 minus the base raised to the upper limit of summation plus 1 divided by 1 minus the base. Okay, so simplify this right-hand side, you get b to the n times 1 over 1 minus b over a, minus, so these have the same denominator, so the difference will have the same denominator. And then on top I get the 1 canceling the 1 here, and the negative canceling the negative there, and so I get positive b over a, all to the negative n. Okay, so I have two different answers here, but luckily they are answers for disjoint periods of time. I have one answer for positive time, I have one answer for negative time. And so if you like, we can combine these into a single answer. They both have 1 over 1 minus b on a, but then in negative time, we have this part. So that's a to the n u of negative n minus 1 plus the answer in positive time, which is going to be b to the n u of n. And again, this only holds provided b over a has modulus less than 1. If that proviso is not true, then actually y of n is infinite for all values of n, and there was really no point in doing this exercise. Okay, so this is, as I promised, a slightly harder example of discrete time convolution, where we are pulling on your knowledge of dummy variables and variable substitutions, as well as the results from geometric sequences and series, to write the output that changes character in negative time as from positive time. And I want that to make sense because the forcing function changes character between negative time and positive time. So we have, in some sense, the forced response in negative time followed by the natural response in positive time. And it's no accident that the natural response in positive time is exactly the impulse response, scaled by this scaling factor. Okay, thanks for watching. The next video will be on properties of convolution, so you can take shortcuts and do all that good stuff. Thank you.